Since the dawn of humanity, we have gazed up at the night sky and wondered about the nature of the universe. The twinkling lights above have always sparked our curiosity and imagination. What are stars made of? How vast is space? These questions have driven us to explore and understand the cosmos. What secrets does the cosmos hold? Are we alone in this vast expanse? Or is there more out there waiting to be discovered? For centuries, these questions remained shrouded in mystery. Ancient astronomers mapped the stars and created elaborate myths to explain the heavens. But with the advent of modern science, we began to unravel some of the universe's most profound secrets. Telescopes and space probes have allowed us to peer deeper into space than ever before. One of the most captivating and challenging frontiers in physics today is string theory, a revolutionary idea that suggests the universe is far stranger and more wondrous than we ever imagined. String theory proposes that at the most fundamental level, the universe is composed of minuscule, vibrating strings. These strings are the building blocks of everything we see and experience. Just as the music we hear is made up of tiny vibrations called sound waves, string theory suggests that the universe itself is a symphony of vibrating strings. These strings are far smaller than even atoms, the building blocks of matter as we know it. They vibrate at different frequencies, creating the particles and forces that make up our universe. These strings are far smaller than even atoms, the building blocks of matter as we know it. They vibrate at different frequencies, creating the particles and forces that make up our universe. In the realm of string theory, these infinitesimal strings are the fundamental notes, and the symphony they create is the vast and mysterious universe we inhabit. Each string's vibration contributes to the cosmic melody. String theory attempts to answer some of the biggest questions in physics, such as the nature of gravity, the origin of the universe, and the existence of other dimensions. Such as the nature of gravity, which has puzzled scientists for centuries. The origin of the universe, a question that has intrigued humanity since the beginning of time, and the existence of other dimensions. Could there be parallel universes or higher dimensions beyond our perception? String theory opens up a realm of possibilities that challenge our understanding of reality. To understand string theory, we must first journey deep into the heart of matter, far beyond the familiar realm of atoms. Imagine taking an apple and cutting it in half, then in half again, and continuing this process until we reach the smallest possible piece of apple. This, we once believed, was the atom, the indivisible building block of all matter. However, scientists discovered that atoms are themselves composed of even smaller particles: protons, neutrons, and electrons. Protons and neutrons reside in the atom's nucleus, while electrons whiz around this central core. But string theory takes this journey even further. It suggests that these subatomic particles are not point-like objects, but rather tiny, vibrating strings of energy. Think of a guitar string. Depending on how it vibrates, it produces different musical notes. Similarly, in string theory, the way a string vibrates determines the properties of the particle it represents. String theory proposes that the universe is made up of more than just the three spatial dimensions we experience in our everyday lives: length, width, and height. In fact, string theory suggests there could be as many as 10 or even 11 dimensions. It's hard to imagine such a reality, but mathematicians and physicists are exploring the mind-boggling implications of these extra dimensions. These extra dimensions, string theory suggests, are curled up and hidden from our perception. Imagine a garden hose viewed from a distance. It appears as a one-dimensional line, but upon closer inspection we see it has a second dimension, curled up in a circle. Similarly, string theory posits that our universe may have higher dimensions curled up at an incredibly small scale, far too tiny for us to observe directly. These extra dimensions are not just a mathematical curiosity. They play a crucial role in string theory's ability to explain some of the universe's most fundamental mysteries. For example, the existence of extra dimensions could help unify the four fundamental forces of nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. The pioneers of string theory, a historical perspective. The roots of string theory can be traced back to the 1960s, a time of great intellectual ferment in physics. This was a period marked by groundbreaking discoveries and intense debates, as scientists sought to understand the fundamental nature of reality. Scientists were grappling with the challenge of reconciling Einstein's theory of general relativity, which describes gravity, with the strange and counterintuitive world of quantum mechanics, which governs the behavior of particles at the atomic and subatomic levels. The quest to unify these two pillars of modern physics was a daunting task, one that required innovative thinking and bold new ideas. In 1968, a young physicist named Gabriele Veneziano stumbled upon a mathematical formula that seemed to describe the behavior of certain subatomic particles. This discovery was serendipitous, as Veneziano was not initially searching for a new theory of the universe but rather trying to solve a specific problem in particle physics. Little did he know this formula would become a cornerstone of string theory. It provided a new way of looking at the fundamental building blocks of the universe, suggesting that they might not be point-like particles, but rather tiny, vibrating strings. Over the next decade, other physicists, including Yoichiro Nambu, Holger Beck-Nielsen, and Leonard Susskind, began to develop the idea that the fundamental constituents of the universe might not be point-like particles, but rather tiny one-dimensional strings. These strings could vibrate at different frequencies, giving rise to the various particles observed in nature. These pioneers of string theory faced an uphill battle. Their ideas were met with skepticism and resistance from the broader scientific community, which was deeply entrenched in the traditional particle physics paradigm. The early versions of the theory were plagued with inconsistencies and seemed to predict the existence of particles that had never been observed. These issues led many to dismiss string theory as a mathematical curiosity rather than a viable physical theory. Despite these challenges, a small but dedicated group of physicists continued to develop string theory, believing it held the key to unlocking some of the universe's deepest secrets. They were driven by the hope that string theory could provide a unified framework for understanding all of the fundamental forces of nature, from gravity to electromagnetism to the strong and weak nuclear forces. Their perseverance and passion laid the groundwork for what would become one of the most ambitious and far-reaching theories in the history of physics. Dimensions unveiled, beyond our perception. One of the most mind-bending aspects of string theory is the idea that our universe may have more than the three spatial dimensions we experience in our everyday lives. To understand this concept, imagine a flat, two-dimensional world inhabited by beings who can only move forward, backward, left, or right. They have no concept of up or down. Now imagine a three-dimensional object, like a sphere, passing through this two-dimensional world. The inhabitants would only see a series of two-dimensional slices of the sphere as it moved through their plane of existence. They might see a point appear, then grow into a circle, then shrink back into a point and disappear. To them, this would be a very strange and inexplicable event. In a similar way, string theory suggests that higher dimensions could exist beyond our perception. These extra dimensions could be curled up at an incredibly small scale, far too tiny for us to observe directly. Just as the two-dimensional beings in our example could only perceive slices of the three-dimensional sphere, we may only be able to perceive a limited slice of a much richer higher-dimensional reality. Unifying forces, the quest for a grand theory. One of the most tantalizing promises of string theory is its potential to unify the four fundamental forces of nature. These forces are the building blocks of our universe, governing everything from the smallest particles to the largest cosmic structures. These forces govern everything from the interactions of subatomic particles to the motion of galaxies. They are the invisible threads that weave the fabric of our reality, influencing every aspect of the physical world. Gravity, the force of attraction between objects with mass. It is the reason why apples fall from trees and why planets orbit stars. Gravity shapes the structure of the universe, from the formation of galaxies to the behavior of black holes. Electromagnetism, the force responsible for electricity, magnetism, and light. It powers our homes, drives our technology, and enables the very act of seeing. Electromagnetic waves travel through space, carrying energy and information across vast distances. The weak nuclear force, the force responsible for radioactive decay. It plays a crucial role in the processes that power the sun and other stars, as well as in the mechanisms of nuclear reactions and particle interactions. The strong nuclear force, the force that holds the nucleus of an atom together. It is the glue that binds protons and neutrons, overcoming the repulsive force between positively charged particles to create the stable nuclei of atoms. For centuries, Physicists have dreamed of finding a single, elegant theory that can explain all four forces as different aspects of a single fundamental entity. This quest has driven some of the greatest minds in science, from Newton to Einstein, and continues to inspire researchers today. This elusive goal is often referred to as a grand unified theory or a theory of everything. Such a theory would provide a comprehensive framework for understanding the universe, uniting the forces that govern the cosmos into a single coherent picture. String theory offers a tantalizing glimpse of such a theory. It proposes that the fundamental particles we observe are not point-like dots, but rather tiny, vibrating strings. These strings can vibrate at different frequencies, giving rise to the various particles and forces we see. In string theory, the different vibrations of strings could potentially give rise to all four forces. Just as different musical notes emerge from the vibrations of a guitar string, the fundamental forces and particles of the universe could be the result of different vibrational patterns of these tiny strings. Just as a single guitar string can produce a wide range of musical notes, a single type of string in string theory could, in principle, give rise to all the forces and particles in the universe. This elegant idea suggests that the complexity of the universe might arise from simple, underlying principles. This unification of forces is one of the most compelling reasons why string theory continues to captivate the imaginations of physicists around the world. The quest for a grand unified theory is not just a scientific endeavor, but a profound journey to understand the deepest truths of our existence.